So now let's come to the sizing. If I have a footer device, what should be the size of my NMOS transistors? Yeah, exactly. This is right. So I will say 2, 2. Header device should be 1. I don't need to size that up because remember, my header device is not playing any part in the logic evaluation. Evaluate phase is the only place where logic evaluation happens. So now first question before we even go ahead and evaluate logical effort. What is the pull-up logical effort of the circuit? Huh? It's an irrelevant question because in the pre-charge phase the output has been pulled high already. Logical effort is some estimate of how long it will take for the output to go high or low, right? But for the output to be high in a dynamic circuit, you have to only look at what happens in this evaluate phase. By the time you are at the evaluate phase, the pre-charge has already taken it high. So therefore, there is no delay in taking the output to a logic high, and therefore pull-up logical effort is irrelevant in this case. It's not zero. It's irrelevant. Okay. So GU, right? Not relevant here. So what about GD, pull down logical effort? You got to take the ratio of input gate capacitance to the gate capacitance of a symmetric static CMOS inverter. You have to construct that inverter, right? So what is the gate capacitance of this guy? CA to C, exactly. Now, what is the pull down strength of this gate? Or how do I construct the reference inverter for pull down logical effort? So if I have a capacitor here, what is the current coming out of the load capacitor during discharge? I. This is I. And therefore, I have to look at an inverter which can provide the same current as that. So therefore, this has to be I. Which means this has to be how much? 1. If this is 1, what's the PMOS? 2. Therefore, CA here, CA prime is how much? 3C. Therefore, what is the pull down logical effort? 2 by 3. Clearly, this is a number that is less than 1. So it's faster than your static CMOS inverter whose logical effort is 1. Now, if I did not have the footer device, what would be my logical effort? Let's say I could impose an additional constraint apart from the fact that the input cannot fall, right? I also impose a constraint that in the pre-charge phase, I will ensure that the input is not high, let's say. Then I can do away with the footer device. So what will be the logical effort in that case? 1 by 3, exactly. So without footer device, GD 1 by 3. Okay. Now how do I construct a NAND 2 gate? Yeah. Yeah. Yes. Yeah. Correct. Exactly. But it's possible. Like in memory circuits, it is possible. For example, I know that during this entire phase, my word line only has to turn on, right? Then the input just goes high and it's going to remain high forever after that. Those kind of things I can do with this kind of a circuit. Okay. What about NAND 2? The NORs are the most useful. Okay, we'll come to that. But how does a NAND 2 gate with a footer device look like? My clock. Again the clock. So what's the size of my PMOS transistor first? 1. NMOS 3. Right? 3. What's the logical effort now? This is A, B. What's the logical effort? GA equal to GB. Huh? 3C by 3C. Correct? You get 1. So a NAND 2 gate which had 4 by 3 is now down to 1. Clear? Now what about NOR 2 logic? Again, one footer device, header device connected to the clock output. Now I need to have parallel logic here. A, B. This is my normal NOR gate. If I wanted a dynamic NOR gate without a footer device, it would be this. Now I add a footer device. Sorry, this is an NMOS. Again connected to the clock. So what's the size of the transistors now? Sorry? PMOS is how much? 1. NMOS 2 and 2. What if I made this NOR 3? Same thing, right? C, right? NOR 3, then this would be again 2. So what's the logical effort now? GA equal to GB equal to GC. How much is it? 2 by 3. What is it? Is it 2 by 3 irrespective of number of inputs of the NOR gate? It is. That's the biggest advantage of a dynamic NOR gate. What would otherwise scale as 2n plus 1 logical effort is now simply going to be 2 by 3, a fixed number irrespective of number of inputs. Clear? Any questions here? Yeah. Pseudo? Correct. Their NAND will be constant. If you're talking of if I do a pseudo PMOS, right, where I put an NMOS transistor below and the PMOS network remains as it is. Yeah, there of course the NAND will basically have the same logical effort. You're right. Correct. Okay. So clearly this logical effort is lesser. And what about the parasitic effort? Let's say that parasitic effort, I'm just going to count the diffusion capacitance. What's the diffusion capacitance on the output? 4C, right? So what is the parasitic effort here? 4 by 3. What about here? This is 7C Now what happens if I increase the number of inputs to the NOR gate? So that clearly is going to go up linearly with the number of inputs. Parasitic delay does depend on the number of inputs. It's only logical effort that is less. But remember, parasitic effort is a constant number that adds to that delay optimization problem. It's the logical effort that ultimately determines gate sizing. Therefore, logical effort is more important than the parasitic effort, and if that is constant, that's a big advantage. Okay, so therefore here parasitic effort will simply be how much? 7/3. And of course, remember, I have not indicated explicitly, these are all only for pull down. I have said GA, GB, GC, it's actually GAD, GBD, GCD. Right? Pull up is irrelevant in this case. Okay? Now great, I have a dynamic inverter, I have a dynamic NOR gate, I can make any dynamic circuit that I want. So next, what do I want to do? I want to cascade these gates. So I'll take let's say I want to build a dynamic AND gate. Okay, what do? I'm going to connect a dynamic NAND gate, A, B, 5. Right, and I'm going to connect it to the clock here. This is my inverter. This is my footer clock. Y. I want Y equal to A into B. This is what I want it to behave like. Will this circuit work? So what are the constraints on the input A and B? It can only rise, right? It cannot fall, right? That's a monotonicity condition. The signal can be monotone, non-decreasing. It means it can remain flat or it can rise. It cannot fall, right? That's the constraint. So since it's a dynamic NAND, I would have ensured that A and B do not fall during the evaluate phase. What happens to the inverter? Let's say that both A and B, my clock is here. Let's say that my, for simplicity, my input B is high all through, and my input A went high like this. Okay, this is Y1 and that is Y. What happens to Y1? So again, let's plot this very clearly and carefully. Y1 will be, this is pre-charge phase, this is evaluate phase, pre-charge, evaluate, right? Y1 is logic high in the pre-charge phase. Then input A is 0. So therefore the output will now float high impedance till the input A rises. Then this will fall, right? This is the falling transition that is causing this output to fall, right? That's what that arrow means. This arrow here basically indicates that because that signal was rising, that caused that output to fall. Okay, so Y1 has now, what has it done? It has violated the monotonicity condition on my inverter. Though my inputs A and B have adhered to that condition, Y1 has violated that condition. It's very obvious because the gates are inverting in nature. If I have monotone increasing, then the output is going to be monotone decreasing. And therefore, I cannot cascade two dynamic gates just like that. Right? This circuit will not work. right? And of course, this one is violating monotone non-decreasing condition. So therefore, how do I even use these gates? I have to do something, because if I can't cascade gates, they're completely useless for me. So therefore, the only way to overcome this problem is to put a static inverter between two dynamic gates. Right? So the same thing, I can now get a dynamic AND as by building my dynamic NAND first. A and B. Now here, instead of connecting a dynamic inverter, I will connect a static CMOS inverter. And then I can connect it to any dynamic gate after that. Why is that? Because now if A and B are monotone increasing, output Y1 will be monotone decreasing, but then the output Y here will again be monotone increasing, which is what is going to go to the next dynamic gate. Right? So this is basically called domino logic, cascading a static CMOS inverter with a dynamic gate is called domino logic. You will see why. Domino logic. Okay, so let's look at this. For example, I have this inverter and I'm going to connect it to another dynamic inverter here. And then I'm going to connect another static CMOS inverter and I'll see what the output here is. So this will be Y2, Y3, Y4. Right? So remember that this is my gate. This is one unit. And this is another unit. So these are my two domino logic gates. Domino AND gate, domino buffer. Okay. So let's just draw a waveform with a simple case here. Phi. Let's assume B is equal to 1 always. Let's assume, okay, I'm not drawing that. B equal to 1. A is going monotone increasing somewhere here. What will happen to Y1? Y1 will float first when the clock turns off. Right? I mean, initially in pre-charge, of course, it's pulled high, then it will float and then it will fall. This will cause the transition. What happens to Y2? In the pre-charge phase, Y1 is what? High. So Y2 will be low. Is it floating low or driven low? It's driven low. In the next, between the clock and till the input rises, is Y2 floating or is it driven to some logic? It is driven. So Y2, because it's the output of a static CMOS inverter, will never float. So this will basically be 0 till here. When Y1 falls, this will rise. This will cause the transition. Right? Now what happens to Y3 and Y4? Let's plot these two again carefully. Yeah. No, I agree. But like he said, right, there is one pull-up path. See, now there's a leakage path to VDD also. PMOS is off. NMOS is also off. So there is one pull-up path to VDD, pull-down path to ground. So these two will cause it to come and settle slowly at some point. It can't go below that. You get the point? It is floating, yes. So it can't be at VDD always. But what's the final value? Final value is there is an off PMOS, there is an off NMOS between VDD and ground. So these two leakage currents have to be the same because it's a series part. No, here, okay, multiple NMOS I understand. Suppose, assume a trivial case. Assume the simpler case where there's a PMOS and there is only without a footer A. So what is happening is there is a capacitor here which is floating at VDD, right? VC of 0 minus. Now there is a pull-up path to VDD because that through leakage of PMOS. Then there is a leakage through NMOS. These two are going to fight and the eventual value will actually not come down all the way to 0. It will come to some intermediate value between 0 and VDD depending on these two leakage currents fighting. Yeah. Correct. So you're right. If it goes below VIH, it's a problem. However, generally at the speeds that we operate at, the clock is not going to be very, very slow. It can't be 1 hertz. 1 hertz is such a limiting case that I gave as an example. Usually you operate this at gigahertz or megahertz. It can't discharge that fast because leakage is such a small current. But you're right that because of this, I cannot operate a dynamic circuit at any frequency. Static CMOS logic, I can operate at any frequency. It will work. Dynamic logic, it cannot work because of this issue. Okay? Anyway, now let's plot Y3. Y3 in the pre-charge phase. This is pre-charge, evaluate, pre-charge, evaluate. In the pre-charge phase, Y3 is now going to be, yeah? Just look at Y3. This is Y3. It's going to be driven high through the pre-charge transistor. Let me call this P1, P2. It will be driven high through the pre-charge transistor P2. And therefore, it's going to be high. Now, what will happen after pre-charge turns off and Y2 has not yet turned on? It will float. So here, this will basically float at VDD. The moment Y2 turns on, it will cause Y3 to discharge like this. Correct? And therefore, Y3 will go low. And this is the transition that's causing it. What about Y4? Y4 again is a static CMOS output, so it can never float. When Y3 is high, it will be low all through till here. Y4 will just be low. Then once my Y3 falls, this will go high. Now you look at what is happening to Y2 and Y4. Now if I cascade many such gates, you have Y2, Y4, Y6 and so on. Basically, just like a domino, the outputs will keep sort of rising or falling. If you look at Y3, they'll all fall. So it's just like a domino. You knock one guy off and everything will go. That's why this is called a domino logic. General. Okay, Y4, the output of the static CMOS logic will keep rising. Okay, any questions here? Yeah. True. See, therefore, the moment I start making a circuit, then there is a spec that has to be met. It's not how many you have to put. You have to size these so that they meet a timing constraint. I can put any number as long as I can size it so that they can meet the timing constraint. Yeah. Correct. True. Absolutely. But the logical effort is much lower there. So therefore it's still sort of okay. You're right. Okay. Okay. Before I proceed, what kind of inverter should this inverter be? These two. Symmetric static CMOS or what? What's the constraint on Y1 and Y2 and Y3? Exactly. Y1 and Y3 can only fall. Therefore, Y2 and Y4 can only rise. Which means all I have to do is make these two as high skew. So I'll gain even more on the logical effort, because on the high skew, that was what, 5 by 6, is it? What was it? I don't remember. 5 by 6 or 2 by 3 or something like that we got. Correct? So the logical effort will be less than 1 even for those guys. Okay? So just to address the question that, he's been worried about this output falling for a while, right? And it is indeed a concern. So how do you get rid of this problem? So the way you do it is, anyway, since I'm going to cascade one inverter after the dynamic gate, what I'll do is I'll have my clocked circuit here. I'll implement whatever pull down network depending on the circuit or the logic that I want to implement. And then I want to put a high skew static CMOS inverter here, right? Now I'll just put another PMOS like this. What is the advantage? When the clock is in pre-charge phase, this output, right, during pre-charge, clock equal to 0. My output of the dynamic gate is going to be 1. Therefore, the output of my inverter will be 0. That means this PMOS will be turned on, right? And therefore, it's going to simply pull this output along with this guy. Both these guys will pull it up to logic 1. Okay. Now, I go to the evaluate phase. Eval phi equal to 1. What happens? This guy is cut off. Now, until the pull down network turns on, this output earlier used to float. The output of my dynamic gate used to float. But now, because there is this PMOS transistor which is cross coupled, right? The output here is floating at 1 now. But the inverter is inverting that logic and causing the PMOS to still pull it up to 1. So the output now never floats. The output will always be will be driven to logic 1, even in the evaluate phase. So now technically I can slow down my clock how much ever I want, because it's being driven. The only constraint is, when my pull down network turns on, it has to be strong enough to overcome that PMOS that is pulling it up, right? So in the evaluate phase, when the pull down network is active, okay, let's just look at this part of the circuit. Let me look at this part of the circuit. Okay, I'm going to have a PMOS that, no, I'm going to have a PMOS that is driven, and let's assume that I'm implementing an inverter. In the eval phase, this is 1. The footer device is turned on. Phi equal to 1. This output is going through a static, high skew inverter and driving this. So let us say that this input went from 0 to 1. A went from 0 to 1. When it is 0, my output Y1 was driven high through this PMOS, through the keeper. This is called a keeper device. But when my input A goes high, see what's happening. There is a path which is trying to pull this down through the NMOS network. There is a path from the PMOS network which is trying to pull it up. Right? So there is a fight. This Y1, you have to size the devices so that the NMOS network can overpower that PMOS network. Which means as long as Y1 falls below VIL of that inverter, that is enough for you. Because when Y1 goes below VIL of the inverter will trip and flip. So when Y1, let's say Y1 was like this and it went below some logic. And let's say this is VIL. At this point, the inverter will trip and the output will go to logic 1 there. Y2. So this is Y1, this is Y2. The moment it crosses VIL, Y2, which was basically 0, will now flip and go to logic high, thereby turning that keeper device off. This is very, very similar to what we did in CVSL logic. We put a cross-coupled thing and that output basically turned off that keeper. Right? The guy was just competing with the pull-down network. Similarly here, this weak keeper will get turned off because the pull-down network is strong enough to overcome the keeper device, and therefore this is not just a keeper, it has to be a weak keeper. Okay, so if this is size 2 and 2, then you would want to size this to maybe 1/3 or something like that. That is the typical number. The idea for a weak keeper is instead of allowing it to float, you weakly hold it up. That is enough. Then I can slow down my clock. Even if there is some noise coupling, nothing will happen. Right? Question is, can I make a transistor with size 1/3? For logical effort discussion, it was okay because whether it's 1/3 or 1, it doesn't matter as long as the relative sizes are okay. So it's fine. But in reality, if I want a transistor with 1/3 and that's not possible, then what do I do? Then you have to use the idea that you can put 3 transistors in series. Right? Each of size 1, 1, 1. This will effectively be like a single PMOS transistor with size 1/3. This is how you make a weak keeper device. Now the problem is, you see the loading on this guy. Ultimately, I have to optimize for delay. The loading on this node Y2 is too much because it's now going to 3C capacitance. Right? So what you do is you simply break this and say, well, I will connect only this. These two I will just ground. As long as one transistor in that series path is cut off, it is enough. Right? Here I am reducing the capacitance, but also achieving my weak keeper to be 1/3 kind of size. Okay? So this is the idea behind a weak keeper. So I urge you to go back and redraw this timing diagram that you have here. If I also had a weak keeper, all these floating nodes will vanish. They will all become driven high values. Clear? Okay.